Okay, um, welcome to the last part of this chapter. Okay, we will finish this chapter about determinants with an application. So, section 6, application. Okay, here we'll see Cramer's rule. Okay, and let's start with the theorem of Cramer's rule. Okay, the theorem says the following. Let ax equal to b be the matrix form of a system of n linear equations in n unknowns where x is equal to x1, x2, xn, t. So if determinant of a, okay, if a is non-singular, so if determinant of a is not equal to 0, then the above system has a unique solution and for each k is equal to 1, 2, and we have xk is going to be equal to determinant of mk over determinant of a, where mk is the n by n matrix obtained from A by replacing column. I will explain all of this very shortly. Column k of A by B. Okay, so let me explain this. We'll do one example shortly, and here is our example. Okay, so the example we are going to do says the following. Example. It says using Cramer's rule, solve the following equation. Okay, so we have 2x1 plus x2 minus 3x3 equals 5, and x1 minus 2x2 plus x3 equals to 10, and 3x1 plus 4x2 minus 2x3 equals 0. So what does Cramer's rule tell us? It says, okay, first of all, let's get matrix A of this linear system. So basically the linear system is equivalent to AX equals to B. Okay, so let's get A and B. A is going to be the matrix formed by the coefficients of these unknowns. So we have 2, 1 minus 3, 1 minus 2, 1 and 3, 4 minus 2. Okay, so 2, 1 minus 3, 1 minus 2, 1 and 3, 4 minus 2. And B is the constant, is formed by the constants here. So we have 5, 10 and 0. So we will assume, okay, so Cramer's rule or the theorem says if determinant of A is different from 0, so that means if A is non-singular, then the system has a unique solution, and the solution xk, so we have 3 x's here, so xk here is going to be determinant of mk. We will see shortly what how to get mk is equal to, so the solution of xk is equal to determinant of mk over determinant of a, and mk here we can get our m1, which is, it says we have how do we get m1? We get the matrix 1, but we replace the first column with b. So m1, we are going to replace column 1, okay, with b. So instead of 1 3 2 3 1 here, we are going to write 5 10 0, but we leave the rest, the two other columns the same. So 1 minus 2 4 minus 3 1 minus 2. So let me show you properly. So mk is going to be equal to 5 10 0, sorry, m1. Now let's find, okay, let's get m2. In m2 we are going to replace, so we use the matrix A, but we are going to replace the second column with b. So let's write the first column down, and the third column minus 3 1 minus 2, but we are going to replace the second column with b, so 5 10 0. Okay, and m3, in m3 we are going to replace the third column. So we have 2, the first two columns are going to be written down as the way they are. 2 1 3 1 minus 2 4, and third column is going to be 5 10 0. So this is how we are going to use Cramer's rule. So first of all, we need to write down the A matrix, we need to write down the B vector, and then we need to write down, sorry, m1, m2, m3. So x1, okay, let me go to next page. So Cramer's rule says x1 is going to be determinant of m1 over determinant of A. Okay, and x2 is going to be determinant of m2 over determinant of A, and x3 is going to be equal to the determinant of M3 over determinant of A. So basically what we have to do next is to find determinants. So let's find determinants of A. So let's find determinant of A, determinant of M1, okay, M2, and determinant of M3. Okay, so we know how to find determinants. We can either use Gauss's method or Laplace formula, as you have seen, using the multilinearity expansion is very demanding. So mostly we don't use multilinearity expansion to find determinants. Okay, we mostly use Gauss's method, but in some cases Laplace's formula is more suitable. Okay, but here we are going to use just Gauss's method. So we have the first our A matrix, which is equal to 2, 1 minus 3, 1 minus 2, 10. Sorry, just small mistake here. A matrix 2, 1 minus 3, 1 minus 2, 1 and 3, 4 minus 2. Let's do Gauss's method. Okay, so we have minus a half rho 1 plus rho 2 is going to be equal to 2, 1 minus 3, we have 0, minus 5 over 2, and 5 over 2 there, and third row, let's do minus 3 times 3, minus 3 over 2 multiplied by rho 1 plus rho 3, okay, which will give us 0, 5 over 2, and 5 over 2. Okay, then what do? We do rho 2 plus rho 3 to give us 2, 1 minus 3, 0 minus 5 over 2, 5 over 2, 0, 0, and 5. So that means determinant of A is equal to, we have to multiply down the diagonals. I'm sure you know how to find determinant, okay? After the echelon form of the matrix, we just multiply down the diagonal. So we have 2 multiplied by minus 5 over 2 multiplied by 5, which is equal to minus 25. So determinant of A is equal to minus 25. Good. Now we need to find determinant of M1. So here we have M1. Oh, sugar. Pardon, sorry. We have M1 equals 5, 10, 0, 1 minus 2, 4, minus 3, 1 minus 2. And let's do Gauss's method. Okay, so we have minus 2 rho 1 plus rho 2. So we have 5, 1 minus 3, minus 2 rho 1, so we have 0. Okay, minus 2 row 1 plus row 2 is minus 4. Okay, so it's going to be 7. And here we have row 2 plus row 3. I think we can just go step by step. It's better to make things clear. So here we have 0, 4 minus 2. So what we are going to do here is going to be row 2 plus row 3. I'm sure you know how to do Gauss's method. Okay, we have done it. We have seen it in first chapter. So we have 5, 1 minus 3, 0 minus 4, 7, and 0, 0, 5. So determinant of M1 is going to be equal to 5. So we are going to multiply down the diagonal. Okay, just like this. 5 multiplied by minus 4 multiplied by 5, which is equal to minus 100. So M1, determinant of M1 is equal to minus 100. Now let's find determinant of M2. M2 is equal to 2, 1, 3, 5, 10, 0, minus 3, 1, minus 2. So Gauss's method. Okay. Minus half row 1 plus row 2 gives us 2, 5 minus 3, 0, 15 over 2, 5 over 2, 0, minus 15 over 2, 5 over 2. And we have row 2 plus row 3, okay, which gives us sorry, here, okay, we got here by doing minus 3 times 2 row 1 plus row 2, okay, to get the third row. So row 2 by row 3, we have 2, 5 minus 3, 0, 15 over 2, 5 over 2, and 0, 0, 5. That means determinant of M2 is equal to 2, 15, 15 over 2 multiplied by 5, which is equal to 75. That means determinant of M2 is equal to 75. M3 is equal to 2, 1, 3, 1 minus 2, 4, 5, 10, 0. And doing Gauss's method, okay, so we have minus half row 1 plus row 2 will gives us 1, 2, 1, 5, 0, minus 5 over 2, 15 over 2, and here minus 3 over 2 row 1 plus row 3 is equal to 0, 5 over 2, minus 15 over 2. Then we do row 2 plus row 3 to get the following: 0 minus 5 over 2, 15 over 2, 0, 0, 0. So we have seen in one of the lemmas that the determinant of a matrix containing 0 row is going to be equal to 0, and we have proved it in an example in one of the previous videos. Okay, so we have a determinant of m2 is equal m3 is equal to 2 multiplied by minus 5 over 2 multiplied by 0, which is equal to 0. So determinant of m3 is equal to 0. So now using Cramer's rule, okay, we have okay, I think we can squeeze it in here. X1 is equal to determinant of m1 over determinant of a, which is equal to determinant of m1 is minus 100 divided by minus 25. So x1 equals to 4. Okay. x2 is equal to determinant of m2 over determinant of a, which is equal to 75 over minus 25, which is equal to 3. Okay, so x2 is equal to minus 3, minus 3. x3 is equal to determinant of m3 over determinant of a, which is equal to 0 over minus 25, which is equal to 0. So x3 equals to 0. So the final solution is x1, x2, x3 is equal to 4 minus 3, 0. So this system of linear equations has one solution, has a unique solution, which is 4 minus 3 and 0. So we will finish this section with the advantages and the disadvantages of the Cramer's rule. Okay. Yes, we use Cramer's rule to find the solutions of linear systems, but we can't. It's not very practical for any linear system. So okay, we will just finish this chapter, this section, with the advantages. Or when do we use Cramer's rule and when don't we use it? Okay, so Cramer's rule is useful, and but sometimes not practical. Okay, practical. Okay. Cramer's rule is useful when we are dealing with small and simple systems. Okay, systems with coefficients of the matrix being small integers. Okay, we can use Cramer's rule for those systems with small integer coefficient. But when we have big and complex and non-integer coefficients, then we don't use Cramer's rule. Cramer's rule is not suitable. We just use our friendly Gauss's method. Okay. So Cramer's rule is not practical for large or complex systems. Okay, this is going to be the end of this chapter. Okay, and in the next video, we'll just do the summary of the entire chapter, just a few minutes to do a summary of everything we have seen in this chapter. Thank you, and see you in the next video.